Okay, this is a difficult question. There's lots of words, so let's first focus on the action word. And it asks us to calculate the initial rate of a reaction. And it also tells us earlier in the problem that this is first order kinetics. So we know that the rate law is going to be that the rate is equal to k times some expression of amount of x. Don't worry about the fact that x is given to you as pressure rather than concentration. This is going to work either way. However, we do need to know what k is. So we have to find a way to determine k. Looking back to the question, we see we're given information about initial and final amounts in 4 hours. So we can use that to determine what k is. We use our first order integrated rate law, and we're going to solve it for k. So k is going to be equal to ln of at to a0 divided by minus t. Here in the numerator, we take the natural log of a of t is going to be 0.53 atmospheres, the initial 0.71, and minus t, I'm going to use minus 14,760 seconds, as I've done the conversion from hours to seconds. This gives us a rate constant of 1.981 times 10 to the minus fifth, and units are reciprocal seconds. Okay, I'm going to carry some extra sig figs throughout this problem. Now that I have k, I can plug that into our initial rate law and get the rate of reaction, the initial rate of reaction, at the start of this reaction. Okay, so that's rate is equal to k, 1.981 times 10 to the minus fifth, second minus 1, and our initial amount was 0.71. So our calculation yields 1.406 times 10 to the minus 5, and units are atmospheres per second, or with two sig figs, 1.4 times 10 to the minus 5 atmospheres per second. Okay, so the general idea here is we needed to find a means in which to calculate k so that we could apply it to our first order integrated rate law to get our initial rate.